We're going to just keep going. I really want to try to finish chapter 8 as much as we can today. We will go back later and do the AP review questions that we were doing on reading potential energy curves and on the relationship between potential energy curves and forces. I have that scheduled for later this week because we're not ready to do a lab yet in chapter 9, and we've done the labs for chapter 7 and 8. There's a homework due date for the chapter 8 part 2 homework on the portal, I believe. There's a date for the quiz, and we will go over the break homework probably next week as well, because I only want to go over it once. So I would rather that everybody be back. Okay? So we were talking about, just to review things a little bit, because I know the whole point of the break homework was that you weren't going to forget absolutely everything you've learned in the last 4 months, but let me draw your attention to some things that will be perhaps more important. So chapters 7 and 8 are talking about what topic, or what two topics? Work and energy, okay? Power kind of fits in there too, because power is the rate at which work is done. Up until this point, we have only really talked about the changes in energy due to conservative forces. So we've talked about a system where we've had a ball falling, and then really the only force that's acting on that ball is the force due to gravity, and that makes a change in the potential energy. Or we've talked about an object on a spring, and then the force that's making that change is the spring force. But we want to expand that, because life involves external forces. Okay, life involves air resistance, life involves friction, and we want to be able to talk about energy using those things and find that what we can really do is conserve the total energy, and that in many cases we can account for, we can calculate the work done or the change in energy done by a friction force or an air resistance force or some other kind of applied force, and then we can figure out what's going on. So first of all, let's talk about what an external force is. And we're going to talk about this in two different situations. So an external force is going to be a force that's acting from outside the system. So it may be that as the object is sliding down the incline under the influence of gravity, that maybe you are standing here pushing it back up, and you are providing an external force. Okay. So in the case with no friction, and really we're just kind of going to end up looking at the two situations separately and then coming up with one great big way of talking about it. Okay. The work done on the system is equal to the change in the mechanical energy. And what is mechanical energy equal to? Do you remember? Potential energy plus kinetic energy. So this is going to be equal to the change in the kinetic energy plus the change in any types of potential energy. And at this point, we really only know about spring, which is elastic potential energy, and gravitational potential energy. So this is going to be the work done by that external force. Okay. Now, of course, when we bring friction into this, it's going to get a little more complicated. Okay. Does everybody got what they need? Okay. So now let's talk about the case with, okay. Got it? All right. So now let's talk about the case with friction. So we're going to consider a block moving along a rough surface. So this is a rough surface. And what does a rough surface mean? It means that there's going to be friction. Okay? So if I have some kind of applied force, F, pulling the block in that direction, in which direction is the friction force going to be? The opposite direction, because the friction force always opposes the motion. And in this case, it's a kinetic friction force because my block is actually sliding. Okay. We're going to let that be the positive direction just because we have to let something be the positive direction. And since I'm dealing with forces, what do I usually write down next? F net equals ma. So since my block is not jumping up and down and I don't really have any motion in the vertical direction, I'm just going to sum my forces in the horizontal direction. So I'm going to skip a couple steps here, but effectively that's going to give me F minus K, F minus FK. And if my applied force and my friction force are constant, okay, and the friction force is constant, we know what the formula is for that, and I shall tell you that the applied force is constant, then the acceleration is going to be constant too, right? Which is important to me because what can I do if my acceleration is constant? I can use my chapter 2 equations. Okay, so in fact, I'm going to use one of those chapter 2 equations right now. The work done by that external force, we're getting there. Okay, so since I don't know anything about time, I'm going to choose that equation from chapter 2. And the first thing I'm going to do is bring the V0 squared over to the other side. And then I'm going to multiply through by m and divide by 2. Note that little space in between the MA and the D. Because I want you to note that this MA and this MA is the same, so I'm going to substitute F minus FK in for MA. So I'm going to have 1/2 mv squared minus 1/2 mv0 squared is going to give me F minus FK times D. And then I can distribute my d. So I've got 1/2 mv squared minus 1/2 mv0 squared is going to be fd minus fk times d. And now we're kind of getting somewhere. What's this going to be? Change in kinetic energy. I want other things to be work. Okay, work would be equal to the change in kinetic energy if there were no external forces, no friction, no change in potential energy. Okay, so what's this going to be? F times d. The work done by what? By the applied force, okay? So I'm going to call that the external work, which is what I'm solving for, and it's the work done by the external force. And then what's this going to be? The work done by friction. But I'm going to call it something else. I'm going to call it the change in the thermal energy. Because friction, because the friction force, when it causes work, that work is dissipated as heat. Okay? So that means I can say if I bring my delta E thermal to the other side, that the work done by the external force is delta E thermal plus the change in kinetic energy. Now, this whole thing, if you look back at the very beginning at our problem, occurs on a horizontal surface. So is there a change in potential energy? No. So in this situation, delta K is really equal to delta E mac because there's no change in potential energy. And of course, I could expand my problem, and if I introduced a spring, or if I had something that was occurring on an incline, like my original picture was, then I would put that delta U into my delta E mac. So basically, I have that the change in the thermal energy plus the change in the mechanical energy has to be equal to the work done by the external force. So this is really going to change the way that we look at conservation of energy. And we can expand it to include things like friction. Okay. So, of what I'm going to call total energy. Okay. So if we say that the work done by some external force that's not friction is going to be equal to the change in the total energy, which is what E is. That's going to be equal to the changes in all the different kinds of energy that we've talked about. So it's going to be equal to the changes in the mechanical energy, And so this is going to be the kinetic energy and any form of potential energy that might be changing. Plus the change in the thermal energy. So this is going to be the heat lost due to friction. Plus changes in internal energy, which is really something you're more likely to come across in chemistry, but we include it here. I cannot think of an example where we actually have a change in internal energy, but it could happen if something changes state. So you need the heat to melt the ice block as the ice block is sliding down the rough surface. I mean, we could get something really crazy going. So those situations exist, but they're not really something we're going to talk about. I just want you to get the whole picture. Okay. So for an isolated system, no energy can leave or enter. Okay? And remember, isolated means there are no external forces. So the energy can only change forms. Yep, so the change in the total energy is going to be zero. And what we really can have, though, is changes in the mechanical energy, changes in the thermal energy, and changes in the internal energy. And like I said before, we're mostly going to be concerned with changes in mechanical energy and changes in thermal energy. Okay? And you can do this a couple of different ways when you're solving problems. You can either say that the changes in the energies have to equal zero, or you can compare the total energy at two different positions or two different times, depending on what the problem says, and know that that total energy has to be equal at any time, at any place within your isolated system. Okay? And just to be complete, we should talk about power for a minute. Because now we can say, recalling that power is equal to the work divided by the amount of time it takes to do that work, that we can talk about the changes in the total energy, not just the changes in the mechanical energy. And then the instantaneous power is the derivative of that expression for the total energy. Okay. You good? You got it? Tough. We're teaching class right now. All right, so let's do a couple examples. Page 206, number 49. That would be lovely, Elisa, if you read it. Okay, so let's draw a picture here. We start with our lodgepole pine. You have all probably seen a lodgepole pine. It is a very straight, very tall pine tree. Okay, you can think about it as a telephone pole. They may now be used for telephone poles, actually. The Native Americans used them as that big long center pole down their longhouses. Okay, so we've got a very long tree, but as you know, is that tree, you've seen a pine tree, is it rough or smooth on that pine tree? Rough. Okay, so we're going to have friction involved in here, which comes into play in a later question. So we've also got our little bear. It's hard to draw a bear. It's got a little ear. Well, and there's something wrong with it looks more like a beaver, but it's better in my picture. But there's something wrong with okay, you just draw a circle. Okay, so that bear starts from rest, and he starts up here, or she, at some initial 12 meters. And where does the bear end up? On the ground. And let's let the ground be equal to what? 0. Okay. That lets a whole bunch of things be equal to 0. And as the bear falls, of course, the bear will accelerate. And she ends up with a final speed of what? 5.6 meters per second. Okay. So this VI and this VF are speeds. Okay. Correct. If it was a velocity, then VF would be negative. Okay. So what does part A ask us to find? Okay, so we're supposed to find delta UG, which means that we need to add what to our picture? Where potential energy is equal to 0, and where should potential energy be equal to 0? On the bottom. Okay, because that's where Y is equal to 0. So just so that we all remember, what's our formula for gravitational potential energy? mgy. Okay. So if I'm supposed to find the change in gravitational potential energy, that's going to be mg delta y, or mg y final minus y initial. When you're doing one of these problems and you're focusing on what the change in the energy is, as opposed to comparing two positions, you really need to make it very clear what the initial state is and what the final state is, because it will change the SIGN sign of what you're doing, and it may totally throw things out of whack. Okay? So, what's the mass of my bear? 25 kilograms. G is Y final is what? 0, and Y initial is 12 meters. So what's delta UG going to be? Negative 2,940 joules. Okay. We'll keep that around, but how many sig figs do I really have here? 2. So how might I write that if I'm going to take sig figs into account? Yeah, but if it's 2,900, then what about those zeros? What is it, Maddie? Negative? But they could be. But you don't, but if you, we wouldn't put a decimal at the end. You really want the decimal to go here, but you can't put a decimal there because that would change what the number, what the value was. This number here could have 3 or 4 sig figs, and it's supposed to have 2. This just happens to be a 0, but it might be significant. So that's every once in a while, I just like to remind you. Okay. All right, somebody read us part B. Okay, so I'm going to go to a different slide here. Basically, part B is asking us to find K final, right? Ooh. Okay, so how do I find K final? Right, so how else would I find K final? 1/2 mv squared. It's a good formula to know. Okay, but of course it's going to be V final. So again, I've got 1/2. What's the mass of my bear? And what's V final? 5.6 meters per second. Remember to square that. And what do we have for K final? Okay. Again, we'll keep that around because I'm going to be using it in part C, but what would that round to? Okay, because I've still only got 2 sig figs. Now, the problem at this point doesn't ask you for the other things I'm going to ask you for, but I, being an omniscient narrator, know that we're going to need it. Okay, so for instance, what's K initial going to be? 0. How do you know K initial is equal to 0? Right, because my object is starting from rest. So that means that delta K, which is going to be K final minus K initial, is going to be the same thing as K final, which is that 392 joules, or if we take sig figs into consideration, 3.9 times 10 to the 2 joules. Okay, we good? We there? All right, so somebody read us part C. Okay, so what's the average frictional force that acts on the sliding bear? So how is that going to relate to all of the stuff we've been talking about? Okay, so it's going to be related to the changes in energy. That friction force, because it's acting over a distance, is going to do what? A force acting over a distance is what? Yeah, it's work. Okay, so force acting over a distance does work. When it's work done by friction, what do we call it? The change in thermal energy. Okay, so that leads us back to that formula that we were talking about a couple slides ago, which says that the change in the total energy is going to be the change in the thermal energy plus the change in the mechanical energy plus the change in the internal energy. So there's not going to be a change in internal energy. This is probably the last time I'll write it. This is going to be delta K plus delta UG. And then this is going to be the work done by friction. Now, if I've accounted for all of my forces, which I have, it's the gravitational force that's making the bear slide down. So that's not an external force. It's the friction force between the bear and the tree that's causing the work done by friction. So that's not an external force. So basically I can say that delta E, the change in total energy, is 0. So that's going to be delta E, so that's going to be equal to delta E thermal plus the change in kinetic energy plus the change in the gravitational potential energy. So the change in the kinetic energy was what? We'll leave it as 392 at this point because I'm making a calculation, and when I'm using an answer I've already calculated, I like to keep an extra sig fig or two around so that I don't have rounding errors. And then what's my change in gravitational potential energy going to be? Okay. So if I do that math, the 392 minus 2940, what am I going to get? No, that's not right. What is it? Maybe I just misheard you. Oh, because you're subtracting 400? Oh, maybe. It doesn't matter. The answer that I get when I round for what I want to round for is that. Maybe I'm wrong. Maybe I've been wrong all these years. I've been wrong all these years, which is interesting. No, it doesn't. It doesn't round the same at all. In fact, I think what I did was, yeah, I took 2,900 minus 390 and got 2,510. It does not round to the same thing. We'll leave that there for the moment. We'll leave that there for now. Okay, and you're right. If I'm rounding to 2 sig figs, I get the same thing. You could be an astronomer's out because really all those numbers are 2 as far as an astronomer would be concerned. So you'd be doing great. Maybe 3, but you know. Okay, so that tells me that delta E thermal is equal to 2548 joules. But am I looking for delta E thermal? What am I looking for? Yeah, so how does that fit in here? Right. Okay, because remember that the delta E thermal is the work done by the friction. Friction's a constant force, so I can let the work done by friction be Fk dotted with D. So that gives me Fkd cosine theta. What's my D going to be? 12 meters. Cosine of what? 180. And that's going to be equal to, and we lost our negative sign. Oh, no, we didn't. 2548 joules. So that tells me that my friction force is going to be what? With all the rounding and everything, we should get about 210 newtons. Okay? We will do some more problems when we meet again. Yeah.